and give me whatever number of workers I ask for. And based on that, ML engine will go and figure out how to acquire those machines and do the spin up TensorFlow on those machines and run the training. So this one is trained at scale in cloud with a dash dash cloud parameter. And now I can evaluate and see how my model is doing. It's the same metric, the same set of steps for doing batch prediction and comparing the results. But my root mean square error has gone down from 3.6 to 3.4, below 3.4. Now that might seem like a small improvement, but in a business problem, even small improvements lead to significant cost savings or revenue increases. So it's really important to have that capability at your fingertips, where you can quickly iterate, get a feel for your model, and then run training at scale, the way we've done. The next interesting part to see is, once I have this model and I'm happy with it, let's say I'm happy with my deep neural network, then I want to move on to the final step, which is I want to deploy this model. This model can be easily deployed with a simple command, just like in other cases for training and prediction. All I say is %% model deploy, and then Data Lab will take the model, create a deployment using machine learning engine, and the machine learning engine will take care of predictions for you and handle scaling and all the good things that are needed in order to have a ready-to-go endpoint that can take an example or piece of data or row and return the results. In this case, take information about a ride, like start time and start location, end location, and predict the fare. So this is, in a nutshell, the entire life cycle. Let's quickly look at what the life cycle was. It was all the way from exploration to prediction. There is one part that I want to cover in addition to this life cycle, which is how to explain the results. For that, I'll use something a little simpler and colorful, which is a different problem set. In this case, instead of doing regression, I'm doing multi-class classification. Effectively, given a picture of a flower, my model is going to predict whether it's a daisy or a rose or a dandelion or some other kind of flower. And so it's a deep learning problem. I've already got a model and I've run the prediction against it, again, using the same command, %ML predict. So same sort of simplicity that will let you do a whole step in a life cycle with a single command with a few parameters. Now in this case, it's good that I have predictions, but beyond that, I can also see how I can explain why those predictions are the way they are. So let's take a look at one of the common examples. Before that, let's look at the confusion matrix. Confusion matrix is an easy way of understanding how much confusion is there in the model between a correct result and some other possible result. For example, daisies are mostly predicted as daisies, not surprising, that's what you would expect. So I have a dominant diagonal, and then off diagonal are the confusions that the model has, where it says, oh, no, the daisy is really a dandelion, or dandelion is daisy, and so on. But this doesn't tell me the whole story. I want to understand why it's doing that. It tells me the quantitative information, but it doesn't tell me qualitatively why it's doing that. So we added an extra capability called explain. It's again done in the same way with a single command, %ML explain. It uses an open source package called Lime, which lets you understand how the particular model is predicting. Roughly speaking, what Lime does is it perturbs the images, figures out how the prediction is running on different perturbations of that image, and then figures out what part of the image is causing the prediction to be what it is. So in this case, for a daisy, you can see that this bright yellow outline on the image that I'm tracing out, this is the region of the image that caused my model to say that it's a daisy, which means it effectively did not use the rest of the image in order to predict. Now that may or may not be okay. It depends on your problem. But you can look at it, visually understand why your model is doing what it is. This is really important because in many cases you might be getting results that look good but for a completely wrong reason. The apocryphal story here goes something like this. A neural network given the task of distinguishing between dogs and wolves was achieving 100% accuracy. And that was on the evaluation data. But when they threw a real example at it, it failed. And they weren't able to understand why. And it turns out that their training data was biased. Training and evaluation, that data was biased. They had snow in all the wolf images, but not in dog images. So the neural network was simply detecting the presence of snow and saying, hey, it's a wolf. Sounds great until you see the explanation. And if you were to see this kind of explanation right away in front of you that said, look, it's looking at snow and saying it's a wolf, you would know, hey, that's not doing the right thing. I need to go back all the way to data collection and get more samples that have wolves without snow so that it doesn't key off of snow, or dogs with snow so that it's not confused based on snow. So that is sort of, even if you leave the apocryphal part of it out, that sort of illustrates the importance of understanding why certain things are happening. And in Data Lab, we wanted to create an experience that not only covered the common case of going from exploration to model deployment, but also covered these kinds of interesting things in between, which is kind of the focus of running this at scale. Now, one part that I did not cover here is hyperparameter tuning. My model, so let's go back to my Chicago taxi example, and let's look at my training. When I set up something like a neural network, I have learning rate, I have some number of layers, number of steps, and so on. These are often called hyperparameters. You can tune them as a data scientist manually. You can pick different values, see which one gives you a better model. Maybe adding an extra layer or going from 7 layers to 10 layers gives you better results. Maybe not. This exploration can be extremely time-consuming and taxing for a data scientist. Instead, what if you could just throw more compute resources at it and run 100 different or 1,000 different combinations of these hyperparameters to find the best possible model? Well, guess what? Machine learning engine lets you do that through hyperparameter tuning with a single call. Well, we won't get a chance to look at the code right now, but let's go back and see the lifecycle all at a glance again. Okay, so this was roughly the lifecycle that we saw, going from exploration to prediction. But in this case, I've added a first step of ingestion, data ingestion, because if you're going to use the serverless capabilities of BigQuery or machine learning engine, the first step is to bring your data to cloud. We have a set of products to enable that as well. And then I've added a few extra steps like managing jobs and models that are also supported by machine learning engine. So this whole set of products comes together, the suite comes together to support you in your task of experimenting with a model, building a model, deploying it, managing it in production, and understanding how to version the models and manage them over long periods of time as well, not just in order to get them running the first time. In addition to that, we saw that entire demo in Data Lab, which lets you do these steps interactively. So you can go back and iterate at any point that you want, look at the results, look at the visualizations like the confusion matrix and a few other curves that we saw. RStudio has already previewed some support for TensorFlow, and that will likely evolve in future. And then you can take all these different steps, put them into a single pipeline to do continuous learning so you can keep improving your models and have a very systematic process in place for getting the most out of your machine learning project. The online prediction path itself can be richer. It's not just about your app sending an example or a row and getting back results. It could be a time series. For example, a time series of pressure sensor values or trades, financial trades that are being performed. And those can be ingested using PubSub and further processed using either Dataflow or Dataproc. Dataproc is our hosted version of Hadoop and Spark. And then machine learning engine can take over the prediction part of it. So with that, we can conclude by looking at the 4 main takeaways. Number 1, there's a lot of opportunity. We are at an inflection point where many business problems can now be solved using machine learning at scale. We can handle lots of data, lots of complex algorithms. We have tools and serverless capabilities for that. And in fact, that's how we boost productivity, by not requiring you to do the grunt work of setting up a database or having somebody in your company set up a database cluster or a machine learning cluster, but simply go and use whatever resources you need for whatever problem at whatever scale. On demand, just get those things ready. You don't even need to figure out how many are brought to bear. If your query takes a few seconds and requires 2,000 machines, that's a lot better than having 20 machines sitting there idle most of the time and then taking a long query. Once you've got your model or your analysis done, then we have the ability to operationalize that. That's an important step to keep in mind because data science is hard, but it's different from doing operationalization. And that is a different set of skills, different set of constraints and concerns. And those are covered by machine learning engine as well. And finally, all of this can be brought to bear in a very incremental fashion. For example, you could add recommendations to your app for the consumer, or you could improve your underwriting process in insurance, or improve your image detection capabilities. It does not have to be the hardest, the biggest problem right away. You can start small, build up expertise in-house and experience in your domain, and then graduate to harder and bigger problems as well. So that, in a sense, concludes this episode of Machine Learning Lifecycle. Thank you for joining us. Please stay tuned for the next episode.
Fantastic. So, interesting. Now, joining us is our audience from AI Track, where they've just finished up on how we can simplify machine learning lifecycle on the whole in terms of exploring data and explaining predictions and, of course, deploying models. So I know, Jay, this is one of your favorite tracks.
This was such a great track because it actually tied a lot of what we're talking about throughout this entire day, right? So essentially took BigQuery, talked a lot about TensorFlow and creating models, talked a lot about exploring that data, and actually talked about deploying that data all within a life cycle. So very cool. Also coming up is on that AI track, we're going to talk about GPUs and cloud TPUs, which are tensor processing units. So you'll find out more in that session. Enjoy.
Welcome back to Cloud on Air, the journey from big data to AI. I'm Zach Stone, the product manager for TensorFlow on the Google Brain team. And this is John Barris, the product manager for Cloud TPUs on the Google Cloud team. Happy to be with you here today. Please feel free to ask questions throughout the presentation. We'll have Googlers standing by to take your questions. We're here to talk about accelerated machine learning with GPUs and TPUs. To give you a quick sense of the presentation, I'll provide some brief context on recent progress in machine learning, or ML. Then John will talk about GPUs for machine learning, and then we'll both say a little bit about cloud TPUs for ML. First of all, the context, this tremendous progress that we've seen in machine learning over the past 10 years. Now, many of you may have heard of deep learning or deep neural networks, and this cartoon I'm showing you here gives you just a sense of how these deep neural networks work. In general, there's input data that comes in. There's a photo on the left here that sort of flows through this series of transformations that are shown as different layers here in this diagram. And the input data will activate different neurons in this model to flow up to a prediction at the top, in this case recognizing that the image is a dog. These networks are trained with millions and millions of different input samples that flow through the network and adjust the strengths of these connections to make better and more accurate predictions at the end. So I want to emphasize this is a very high-level diagram. There are a lot of different details, and these deep neural networks aren't restricted just to imagery. Not only can they learn input images mapped to categories, but they can take input audio, for example, and map that to text. In this case, how cold is it outside, like you might have for speech recognition in an application. They can take text as input and map it to other text, even in another language, for machine translation, which is useful in business and consumer contexts. And they can even take a whole scene, in this case, and describe what's in the scene with a caption, like the blue and yellow train traveling down the tracks. So this is really remarkable that we're seeing this unification across all these different domains, not even just the ones that I've shown you here, but also ranking and product recommendations. Why is this happening now? Well, In the 1980s and 1990s, the last time these neural network approaches were popular, the scale, if you see on the horizontal axis here, scale was much smaller. And so at that time, you'd see these other techniques that were specialized for one domain or another. These handcrafted features for computer vision or for speech recognition would often outperform these more general, flexible, but difficult to train neural networks. But what's happened since then is we've had a lot more compute and a lot more data that sort of moved the bar forward to where we're seeing these general purpose neural networks succeeding across many different domains and delivering state-of-the-art results in a way that wasn't possible in the last wave. So from a product point of view and a business point of view, what does this enable? Well, we're just at the beginning of finding out, but we'll show a few examples. I mentioned translation earlier. It's even possible to scale that translation down to run on device, as we're showing here. This is a combination of computer vision to identify text in the view of the phone, and then to translate that text into another language to help you navigate in a foreign city. Here's an example from Google with Google Photos, but this is applicable in many domains such as image search or product recommendations, where you have large collections of imagery and you want to sort them on the basis of the objects or scenes or people that they contain. This is possible now at an accuracy that's unprecedented. Similarly, in the text domain, with Smart Reply, what you're seeing here is deep neural networks that are processing incoming emails and suggesting responses that save people time on the go. And one thing that surprised us is we're seeing now 12% of all responses sent on mobile are these automated Smart Reply responses, which is saving people a lot of time as they're on the go throughout the day. In the consumer space, these style transfer techniques have used deep neural networks to take an input image in the upper left and then a reference style, as you can see inset in the lower left of all these cases, and transfer that style to the original image to render fun, new, artistic representations of the input photo or painting. Furthermore, on a more infrastructure level, what you're seeing here is detection of text in multiple languages in, I think, street view imagery in this case. And this is really useful for producing more accurate and up-to-date maps and for autonomous navigation, which is really important for the future of transportation. Here's another example of that here. Now, this isn't just limited to photo collections on phones or to images taken from moving vehicles. Also from satellite imagery, you can use modern deep neural networks to identify rooftops, in this case, or other properties of the image in order to analyze which roof spaces would be ideal for deploying solar energy. But there are many other applications of this kind. Back to phones for a second, you can actually take a paired set of input images and depth sensor images to then try to predict the depth from those single images. So this is important for augmented reality and also for improving photography and introducing new kinds of portraits, which, as we all know, leads to better selfies, which we all want. On a more serious note, medical imaging is being transformed by machine learning, where you can take, again, images of the back of the retina, in this case, that are either healthy or diseased, in this case with diabetic retinopathy. And then you can achieve near human level performance in detecting early signs of this diabetic retinopathy, which is a leading cause of blindness. And we hope that algorithms like this will help radically expand access to care and help people avoid blindness all over the world. We're seeing similar results in pathology and radiology, and we think that machine learning techniques are really promising for improving people's health care, as I mentioned earlier. Back to neural machine translation for a second, not just looking at single words or phrases, but actually whole sentences or paragraph. We've seen from going from phrase-based machine translation to the new sort of neural machine translation, we've had dramatic increases from the blue bars where we were before to these green bars that are higher and much closer to human-level quality. In cases where enough training data is available, we're very close to human-level accuracy, and we think this will enable better communication all around the world, both in social contexts and in business contexts. Just to give you an example of translating from English to Japanese and then back to English with these systems, to give you a qualitative sense of the improvement, focus on this last sentence of both paragraphs here. First, the phrase-based version. Whether the leopard had what the demand at that altitude, there is no that nobody explained. It's gibberish. Whereas with the new system, the new neural machine translation system, that back translation becomes, no one can explain what leopard was seeking at that altitude. Now you're missing the word the, but it's much more comprehensible. It sort of captures some of the artistry of the original text. In scientific domains, we're seeing cases in which simulations that are expensive to run, that are currently used to determine prospects of molecules for important applications, can be run hundreds of thousands of times faster once you train a neural network to sort of fit the behavior of the simulation. And we think this is early stage, but could be really exciting in various biological contexts. Furthermore, in robotics, this is early stage work where we're training robots to learn to grasp using a combination of vision and other inputs. And traditionally, robotics has been not learning based. You know, you'll issue precise commands to say that this joint angle needs to be adjusted from here to here, whereas we're just at the beginning of a wave of breakthroughs that we think will enable robots to learn how to move and how to interact with the world and make them much more flexible and robust and useful. So in general, this is just a brief sampling of an age of breakthroughs for machine learning. And so what we want to highlight here today is a crucial challenge that underlies all these different problem domains. And that's that these state-of-the-art machine learning models currently take days or even weeks to train to the highest possible accuracy. Now, the challenge there is if you're a machine learning engineer or you're a machine learning researcher and it takes you weeks to run a single experiment or train a single model, you often will focus only on the highest value experiments. You'll be more conservative in what you try, and you may not discover that next breakthrough technique that's really going to transform your business. What we're trying to do here in Google Cloud and with TensorFlow is to bring that turnaround time down to minutes, or at least hours, so you can have interactive research, instant gratification, and run more experiments and really explore this frontier. So the solution we're talking about today is machine learning hardware acceleration. Now, there's about to be a Cambrian explosion of different types of hardware acceleration for machine learning across all these different platforms and more. CPUs, GPUs, cloud TPUs, mobile devices, including Android and iOS, and embedded devices, all the way down to the Raspberry Pi. What we're focusing on today is how convenient we've made it to access ML hardware acceleration on Google Cloud. I'd like to hand it off to John.
Thank you very much. So I want to talk about a little bit about Google Cloud to begin with. First of all, that we have best-in-class infrastructure, networking, storage, and it's a global networking, storage, and compute infrastructure, and with system-level integration across the board. We have very fast provisioning. When you create a new virtual machine, it can begin running in seconds or less than a minute, even if you have hundreds of VMs you're starting up. We also have security built in, which means we give you granular control over who has access to what resources. And also our 500 security software developers have made this a very secure cloud compared to what you might be able to do on-prem. And then with on-demand pricing, we give you access to a lower capital expenditure. You can bring up what you need for the time that you need it. So let me talk about GPUs for just a minute. So right now we have NVIDIA K80s and P100 GPUs in the cloud. We've promised that Voltas are coming. And we offer both on-demand pricing, and if you use these 24 hours a day, 7 days a week, for a month we offer sustained use discounts for both the K80s and the P100 GPUs. The Tesla P100 is a state-of-the-art GPU, and based on the Pascal GPU architecture. And in fact, it's very high performance for certain types of workloads, especially machine learning workloads. So you can, as we show in this image, you can attach up to 8 K80 GPUs per virtual machine, or up to 4 P100 GPUs per virtual machine. And the nice thing is, again, flexibility is one of the advantages of Google Cloud. You can decide how much compute, how much memory, and how many GPUs you need, and build a VM that has just that right amount of compute, GPUs, and memory. and only pay for what you need. And of course, one nice thing about GPUs in the cloud is you can speed up some of your complex compute jobs. We've talked about, of course, GPUs are used for engineering simulation, but especially for machine learning with these deep learning neural networks, CNNs, that have found so much success today that we've been talking about. That computation power required to do that is massive, and by applying a GPU or a TPU to that workload, you can actually speed up the performance very rapidly. So also, to try out a GPU in the cloud, you can just go to Google Cloud and ask for one and start it up and start running. You don't have to do any installation or do any capital investment, and you only pay for what you need in that case. So some of the key GPU features are that we offer bare metal performance. These GPUs, when they're attached to your VM, are attached directly to the VM through PCIe connection. They're not virtual, which means you get bare metal performance. And as I mentioned before, you have flexibility in how many GPUs you attach to each instance. So if your workload runs best with one, all you need is one, then you can just attach one and pay for that. You can also attach, again, flexibly, GPUs to any machine type, as large or small of a machine type as you want. We offer per second billing like we do for any other VM. And you can add any of the GPU application frameworks you're interested in for machine learning, CUDNN, Caffe, or we'll talk more about TensorFlow, of course. And the benefits of working with GPUs on Google Cloud is that you have access to the latest technology with the backing of our fantastic performing networking and compute technologies. So I mentioned TensorFlow briefly. TensorFlow is an open source machine learning platform that can be used anywhere by anyone. And it's open source, so you can understand whatever you need to about the platform. And in fact, there are GPU benchmarks available with TensorFlow that you can run on Google Cloud. And if you follow this link to the performance benchmarks, then you can test TensorFlow performance yourself. So one example of a company that's using machine learning on GPU instances in Google Cloud is Shazam. And they were able to recompile the index and reimage the instances in well under an hour now using GPUs on Google Cloud compared to their earlier on-prem system. And so the index files are now always up to date, and that's been a big improvement for them. GPUs are available in Google Cloud in 4 regions: US West, US East, Europe West, and Asia East, both K80s and P100s. Now I want to talk about TPUs, and conveniently we have a TPU sitting in front of me. It's fun to see it. You won't be able to touch these when you're using in Google Cloud, but it's fun to see what they look like. We have pictures here as well. First, I'm going to talk about the version 1 of the TPU, which we've been using in Google Cloud since, in the Google system since 2015. And these TPUs were, at the time, 15 to 30 times faster than contemporary CPUs and GPUs, and much more power efficient. But these were designed for inference, for answering questions, not for machine learning training. Then the second generation TPU, which is what we have here today, has 4 chips on a single board with very high-speed interconnect and ultra-high bandwidth memory. So this board provides up to 180 teraflops of floating point performance and has 64 gigabytes of ultra-high bandwidth memory. And this is for both training and inference. And these are designed to be connected together in larger groups as well. So in fact, one thing we've mentioned, we're showing a picture of, is the TPU pods, cloud TPU pods, which have up to 64 of these cloud TPUs interconnected together. And this provides up to 11.5 petaflops of compute. Again, referring back to the image that Zach showed earlier, these deep learning models now can be run very quickly on a pod, so you can get results within hours instead of weeks. And this also includes 4 terabytes of high bandwidth memory. And this is all connected together in a toroidal mesh network. So these will be coming to Google Cloud as cloud TPUs very soon. So some of the key features. I'd like to talk about flexibility. TPUs can be attached to any VM that you need. So depending on how much compute you need to go along with the TPU compute, you can have a larger or smaller VM. It takes advantage of all the networking, storage, and compute performance of Google Cloud. I like to point out that Google Cloud is global, which means if you need to upload data in the US and then share it in Asia or Europe, that data is available in Asia and Europe very rapidly over our fiber network, rather than over whatever pipeline you have in your on-prem facility. We also, these are also integrated with all other GCP products. And they're easy to program with TensorFlow. And you can get, if you just need one TPU, or you can get multiple TPUs if you need it for your workload. So we're going to talk, I'll turn the time over to Zach to talk about TPU use cases.
Sure thing. Thanks, John. Well, we're really excited about bringing these TPUs to Google Cloud as cloud TPUs. And we imagine that several of you will want to use them similar to the way that we do in-house in your cutting-edge R&D labs to develop new products and also new kinds of machine learning breakthroughs, because we think we're still at the beginning of this giant S-curve of machine learning progress. So if you're working with data scientists or machine learning engineers or ML researchers who are basically telling you that they have an infinite demand for computing power, cloud TPUs are a fantastic platform because you can use open source TensorFlow, ordinary open source TensorFlow like you can run anywhere else on-premise or in the cloud, to talk to these amazing supercomputers. Not just individual boards, but soon whole slices of these pods that John showed you earlier. And so the real issue here is increasing the pace of iteration. You know, this is what I was talking about earlier. Instead of waiting weeks or even months for your best models to train, if you can get that down to under a day, you can run multiple experiments a day, you can have a lot more traction on the problem, and you can ultimately provide better recommendations, better products, higher quality speech recognition and synthesis, and so forth to your customers. So once you go from the R&D stage of trying out some new application and you're ready to scale it out in production, well, TPUs are great for that too. That's how we use them in-house here at Google. And so if you have petabytes of training data, or you have an application in which data is streaming through all the time and you need to constantly retrain your model to keep your recommendations fresh and up to date, we think TPUs are going to be a fantastic choice for that training and retraining of these large machine learning models. Often what people are finding today is there's a limit to how many accelerators they can wire together before they get overwhelmed by communication costs. And these TPUs are going to raise that limit a lot, which lets you run more complex and more accurate models, which often translates directly through to revenue on the bottom line if your business is built around, you know, a recommendation or a ranking system. Furthermore, once you've trained these models, you need to serve them at scale, often to large numbers of customers. For example, if we're accepting speech input from, you know, a large number of devices, let's say all Android phones, the fear that originally motivated the TPU program was that if every Android phone user at the time had spoken to their phone for just 3 minutes a day, engineers here were worried we'd have to double the number of data centers. And so these TPUs, because they're so much more powerful, have helped us avoid that cost. And you know, they can help you do much more with less too in this scalable way in the cloud, and handle this huge serving workload of these new, increasingly more accurate and powerful machine learning models. So if you have customers that are speaking, you know, naturally with a product that you're providing, or if you have customers who are uploading images and videos constantly all around the world, and you need to process that input and provide some kind of an interactive response, these TPUs let you run a larger, more complex, more sophisticated model and get higher accuracy responses back in 10 or even 7 milliseconds. So let me tell you just a little bit more about this hardware, because I think it's quite different than the other architectures that people are familiar with today. So under each of these heat sinks, each of these cloud TPU boards has 4 chips, and each chip is divided into 2 cores, as you can see schematically here. Now, each core has a scalar unit, a vector unit, and a matrix unit. And I'd like to say a little bit more about the matrix unit, because that's really the heart of the acceleration that these cloud TPUs are providing. So each core is delivering 22.5 teraflops in float 32. This is not fixed point. You don't have to do any quantization to use this thing. You can just use it in float 32 like you're used to. There's a little bit of reduced precision in the multiplies. And here's a schematic diagram of the systolic array. So remember on the previous slide, I said that this matrix unit is a 128 by 128 systolic array. That's really very large. I'm just going to show you a diagram with a 3 by 3 systolic array for clarity. But imagine the big, massively parallel version of this. So what's happening here is we're able to stage our input data. You take a batch of input data and you stage it in just the right way that's specialized to these matrix computations that lets you do a lot of reuse of the data as your input is streaming in. And so what's happening is computations are sort of flowing through this systolic array, getting reused many times very efficiently to produce the output that you're expecting over here on the right. And so once this gets to sort of 128 by 128 scale, this is an extremely efficient way to do these large matrix multiplications. And it turns out that these deep neural networks are built out of matrix operations. You know, they're all done with linear algebra. And so this turns out to be a great fit for a lot of the large state-of-the-art machine learning models that are underlying all those product and research breakthroughs I mentioned earlier. So very high throughput for matrix multiplications is kind of the message that we want to convey here. I'd also like to emphasize that each one of these chips has 16 gigabytes of HBM2 extremely high bandwidth memory, leading to a total of 64 overall, which is a lot. And we have these extremely high-speed chip-to-chip interconnects that makes it convenient for you to distribute your model across the cloud GPU in either a data parallel way or eventually with model parallelism. So each one of these boards is connected to the host via PCI. And so the mental model when you're using a cloud TPU is roughly the following. As the customer, you SSH into an ordinary GCE VM. And as John said, you can pick any GCE VM you like. And you're running open source TensorFlow there. You can install arbitrary software. You have a lot of flexibility and control. And then TensorFlow is communicating over gRPC with this network-attached cloud TPU. So this is a very flexible configuration. And you can actually build larger networks of multiple VMs and multiple cloud TPUs, and even GPUs mixed in as well. So when you're optimizing models for these cloud TPUs, I just want to give you a flavor of some of the things that need to change. And these changes aren't specific to cloud TPUs. This will be true for the fastest GPUs as well. These accelerators have all gotten so fast that you need to adapt the way you write your model a little bit and improve the throughput of your input data pipeline in order to make sure that you're taking maximum advantage of all the compute you can now get on demand in the cloud. First of all, on the model front, we recommend that people use TensorFlow's new high-level estimator and layer APIs in order to make it as convenient as possible to migrate the program from TPU to GPU or back to TPU. And these estimators and layers provide these high-level abstractions within open source TensorFlow. On the other end, there was a box highlighted called XLA for accelerated linear algebra. That's our compiler that provides these high-performance TPU implementations of common abstractions and common ops and components of deep learning models. So I won't go through the details of the code here. I just wanted to illustrate that moving back and forth from GPU to TPU for a simple model like this is just a matter of adding and editing a few lines of code. On the data side, it's important to mention that these fast accelerators expose new bottlenecks, as I was mentioning earlier, and the data pipeline needs to change in order to keep up. With slower previous generations of hardware, you could overlap your training and your input processing to keep the compute saturated all the time. But once you have way more compute available, suddenly the input preprocessing becomes the bottleneck. And so you want to switch to TensorFlow's new datasets API in order to maximize the throughput of your input pipeline, whether you're feeding NVIDIA's P100 or V100 GPUs, or you're feeding these cloud TPUs. That will give you a lot more throughput. So the code looks simple like this. I won't cover the details here, and that's models, data, all for cloud TPUs. Finally, I'll just say we're really excited about supporting the open research community as well as the commercial audience with cloud TPUs. And so we've announced the TensorFlow Research Cloud, which is 1,000 of these cloud TPUs that we're making available for free via an application process to top external researchers to accelerate progress in open machine learning. So if you're interested in the Cloud GPU Alpha program or in the TensorFlow Research Cloud, you can visit g.co/TPU signup to learn more. With that, I'll hand it back to John for a brief closing statement.
Well, just to remind you that Google Cloud is built on the best-in-class architecture, including network performance, storage, and compute. And now we've added accelerators on top of that. We welcome you to come and try those at Google Cloud. So thank you.
Cool. Well, thank you very much for listening. Please stay tuned for the next sessions. And thanks again for joining the Cloud on Air journey from big data to AI.
In the meanwhile, I think we have the AI track, which is just wrapped up. So again, welcoming our audiences from the AI track, which they just attended, about how they can accelerate machine learning in the cloud using GPUs and cloud TPUs and much more. And
yeah,
yes,
so I think, especially for things like cloud TPUs, as you're talking about sort of accelerating machine learning, the more you can accelerate, the more you can experiment and try, then the faster you can innovate as an organization. And that's why we provide things like that. And that track will also be joining the fireside chat with General Motors and Marriott, talking about job discovery. So thank you very much, and enjoy your sessions.
Yes, and please stay tuned, and you can continue to feed in your questions through the Q button that you see on the right-hand side.
Google's AI building blocks are ready-made frameworks that enable non-specialist developers to rapidly engage machine learning to tackle a broad range of common business challenges. As we'll see, common does not mean ordinary. You put AI on some of these problems and you create an entirely new level of value. Let's look at the Cloud Job Discovery block. It's a way to transform the tough problem of finding and hiring the best possible people. Google applied AI to millions of job postings, creating a new understanding of what employers want in a new hire and what potential employees are looking for. Let's talk with Marriott International and General Motors, two of our newest customers for job discovery, in two very different industries. I'd like to welcome Jessica Lee, Vice President of Talent Acquisition Strategies and Solutions at Marriott, and Suzanne Johnson, Head of Employment Branding at General Motors. Talk about your company in the context of its people needs. What are some of your biggest challenges vis-a-vis hiring?
We are the world's largest hotel company, which means that we have over 6,000 hotels in 110 different countries, and that's a lot of people that we need to hire for all of those hotels. So in any given year, we hire more than 100,000 people per year, so that's a lot of hiring that we're doing, and that means at any given time, we've got over 15,000 jobs open, and so in order to fill those jobs, we've got probably 3 to 4 million different applications that are coming in per year, and millions more who are just simply searching or perusing our career site. So it's a lot of people. And that's in how many languages? How many countries? Over 20 different languages in 110 countries. So when we talk about posting a job availability, we're talking about an immense data problem as well, because you said 12,000 at any given moment openings. That might be described in any number of ways, but there's a Marriott way to describe them that the applicant may not know about. Sure. So I think every company probably deals with this when it comes to a very company-centric way of describing positions or an industry-specific way of describing their roles. Yet we're open to people coming from all sorts of organizations and industries to come work for us. And the example we always like to give is that we have thousands of servers that we employ, and you'll find hundreds, if not thousands, of server openings on our career site right now who are going to be working in our restaurants.
Well, at Google, we have millions of servers, but it's not the same.
Yeah, I mean, those servers can't feed people food, right? They're not going to come out with the dishes. And so someone comes to our career site to do a search, and let's say they're looking for a server job. They type that in. They may get an IT job that is, as a result, that is actually managing servers, but that's not what they're looking for, and that's incredibly frustrating. To go to a website, do a search that doesn't have an experience that you really would expect, that you've come to expect as a consumer, I think it can be incredibly frustrating. And within the HR and recruiting space, we talk a lot these days about this notion of candidate experience. And so, we are great as a company at providing great guest experiences, and it's just become really important for us to focus on the candidate experience. But that also has implications for us as a business. Some of our job seekers are also customers, and if they're having a frustrating experience as a job seeker, they might not have confidence in us as a company from a consumer perspective,
It's a brand experience, too.
Absolutely.
So how does job discovery address this issue?
So when I talk about job discovery outside of the HR and recruiting space, people kind of think it's a no-brainer and are surprised that we're not doing this already. And when I explain, it's making the job search smarter, more intuitive, it's using the power of Google's machine learning, they kind of think, well, yeah, it should be that way anyways. And so we're excited that we're just simply putting in place what people really should expect, powered by Google. That's, what we've been really excited to be able to present to the business. So for our organization, whether you're a hiring manager or a leader, this was something where we really flipped a switch and said, ta-da, here you go, a more intuitive job search. And so really wasn't just me flipping a switch. We worked with Jibe as our technology partner who put in place for us our candidate experience platform. And so for our hiring managers and leaders, really no effort on their end, simply they're just receiving better quality candidates and more quickly too.
So again, it sort of disappeared. They were better at what they were doing in the first place. The AI was like a tool augmenting their own skills.
Absolutely, and it was really important for us that this was a seamless, smooth effort with a partner who really got us in terms of the scope and scale of what we're dealing with from a hiring perspective. It's a lot of data, it's a lot of transactions, and we needed a partner who's going to really make it work.
Now, at this point, there are a lot of solutions in the market that do promise AI in some form or other. How do you sort out the best from the rest?
So yes, like every industry, everyone's got some kind of AI thing that they're shilling, and it is overwhelming and it can be frustrating. So I get calls and emails literally every day from vendors who all claim they have an AI solution, and you really have to figure out how to filter out the noise and ask smart questions to understand what is it that they're offering, and is it really legit and real. And with Jibe and Google, what we were able to really recognize very quickly was that Google has data that you're dealing with on a day-to-day basis separate from job discovery that's immense in terms of just the richness, the history, and then the power of the machine learning. And so it was no-brainer for us. We have confidence in the machine learning that's in place. And what's exciting is that it really helps our job seekers to not have a lot of pressure on them to figure out how does this company talk about certain roles, what's the lingo that they use frequently, and they can just go about their search, get to the right jobs quickly, and apply and hopefully get hired with us.
Tell us a little bit about your company in the context of its people needs.
It's a really exciting time to work at General Motors. We are well positioned to be at the forefront of the personal mobility evolution. And a key to that is obviously having a solid foundation, getting the right people working for the company in the right jobs. The jobs that we're looking for have shifted a little bit over the years. They have gone more into the areas of autonomous engineering, cybersecurity, data analysis. Our big challenge then is to try to make sure that people are understanding what these jobs require so that they can see themselves in these roles or see a match of their skills in these roles. We have always had a large volume of hiring, and some of the areas that we hire in tend to be very big buckets of jobs. So engineering is an example, IT is an example, and within there you can get very specific then in terms of roles. But the way we serve jobs up to date on our site is that you look at things the way we've categorized them. For example, we say it's this type of engineering or it's this type of IT. We don't necessarily get into the specific skills. And in today's competitive marketplace for these types of roles, specific skills are maybe what makes the difference in whether someone is a perfect match or the best candidate for this job. So to be able to input things like skills or abbreviations into a search engine and have jobs come up that match that is a real win for us in terms of getting the right candidate as well as the job seeker who gets a quicker result.
You're talking about people with skills in, say, Python programming or new materials or mapping and navigation. Pretty deep in-demand stuff. There's quite an incentive to speak to them directly and to give them a sense of belonging inside GM to onboard that process very quickly, right?
Yes, exactly. The way I think about it, if a conversation and communication can be more clear from the start, then that's going to build a stronger relationship. So by using this technology on our site, we're starting a more clear conversation from day one.
How does AI and cloud job discovery help you address this need?
We will always have our traditional UX where we're saying these are different job categories and these are the jobs that are under them. But now we put the power back into the job seeker's hands so that they can search for the things that they want to tell us, right? And see how that fit can happen. And like I was mentioning, ultimately, if you're getting a better fit, you're going to get more people that are applying that are going to be interviewed. Better quality of hires, a more satisfied employee because the job that they thought they signed up for is really the job that they're doing. So the hope is that it really does have downstream effect on both the employer and the job seeker's satisfaction.
How did your team react to using AI? And was this a real change of business for them or sort of a continuation of things they'd always done?
Our team was really excited to be doing this because ultimately, our goal is to, when somebody comes to our career site, make it the most efficient, rewarding experience that they can have, because that's ultimately going to make an impression on them about our company. So when it came to this technology, it really is giving us the opportunity to learn more about that job seeker, as well as help that job seeker have the most efficient path to finding a match or a job within our company. So it's really helping us to accomplish a couple of things.
As you start to use this kind of technology, what does it teach you about where HR is going and where you might use AI in the future?
I think it just reminds us that there's always going to be chances to change the way things are done. And just because you've done it one way and it's worked okay doesn't mean that there isn't a better way around the corner. And we really are just looking forward to understanding the potential of this and looking forward to the evolution of what can be happening next, because I really do think this is just the tip of what's going to be done with it.
There's a wealth of opportunity in AI. To fully address the opportunities, we need understanding of data